friends, the topic for today is 80386 Binary Arithmetic Instructions. The arithmetic instructions of 80386 DECREMENT operate on numeric data encoded in binary. Operations include add, subtract, multiply, divide, as well as increment, decrement, compare and negate. In today's video, we'll discuss the arithmetic instructions of 80386 DECREMENT. Let us start. Welcome to our channel Engineering and Technology for You. If you are not subscribed to our channel, kindly subscribe and press the bell icon. Let us start with the introduction. The arithmetic instructions of 80386 DECREMENT operate on numeric data encoded in binary. Operations include add, subtract, multiply, divide, as well as increment, decrement, compare and sign change or negate. And both the signed and unsigned binary integers are supported for the operations. The binary arithmetic instructions may be used as steps in arithmetic on decimal integer, because when we perform the decimal arithmetic, at that time we'll make use of the binary arithmetic instructions, and then only arithmetic on decimal integer will be possible. Then here the source operands can be immediate values, that means the values directly given in the instructions. General registers means any of the registers of 80386 microprocessor. So we have the registers AL, AH, AX, then EAX. So AL, AH, they are the 8-bit registers, AX is the 16-bit registers, and EAX is the 32-bit register. So in this way we have similarly BL, BH, BX and BX and so on. Or the operand may be memory. So memory will be referenced by different base pointer or the source index or other registers. And destination operands can be general registers or memory. Let us start with the first instruction, that is the add instruction. So add integers. So this replaces the destination operand with the sum of the source and destination operand. So here the operation will be source plus destination, that will be going to the destination, and the flags which are affected, they are the overflow flag, sign flag, zero flag, auxiliary carry flag, parity flag and the carry flag. Now let us take some examples of this. The first instruction is add AL, 22. So here 22 is a 8-bit immediate operand. So that will be added with AL and the result will be stored in the AL register. Then add AX, 0100. Now in this case the immediate operand is 16-bit and AX is also 16-bit. So the result will be stored in AX. Then add EAX 22334455. Now this operand is a 32-bit operand and EAX is a 32-bit register. That's why the addition will be 32-bit and the result will be stored in the EAX register. Then add AL, BL, add AX, BX. Now in this case, both the case, here we have the source as well as destination and registers. So AL and BL, these are the 8-bit registers. AX and BX, these are 16-bit registers. So the addition will take place and the result will be stored in the accumulator. Similarly here, these EAX and EBX both are 32-bit registers. So they will be added and the result will be stored in the EAX register. Then add AL, BX bracket. Now in this case, this is referring to memory operand. So the source is memory and the destination is AL, which is 8-bit. So 1 byte from memory will be added to AL register and the result will be stored in the AL register. In last instruction, add BX bracket comma CL. Now in this case, CL is a 8-bit source and BX is memory pointed by BX register. So the addition will take place and the result will be stored in the memory pointed by BX. Then let us go to the next instruction, that is add integers with carry, ADC. Now this will replace the destination operand with the sum of the source and destination plus 1 if carry flag is set. So here source and destination, they are added along with the carry flag and the result will be stored in the destination. But if carry flag is 0 or clear, so the ADC will perform the same operation as the add instruction. It will add the source and destination and the result will be stored in the destination. So ADC instruction is also used to propagate carry when adding integers in stages, because when we are adding a 32-bit if we are using 32-bit add instruction to sum a quad word operand, at that time the ADC instruction. So let us take some examples. ADC AL comma 33. So here the number 8-bit number 33 is added with AL with carry. Then ADC AX comma 1 2 3 4. So 1 2 3 4 is a 16-bit number which is added with AX along with carry. Then ADC EAX 1 1 2 2 3 3 4 4. Now this is a 32-bit number which will be added with EAX along with carry. Then ADC AX comma CX. So AX and CX, they are added along with carry. Then ADC AL comma 4000H. 4000H, this is the address of the memory. So the contents of memory, they are added to the AL register with carry. Then ADC SI comma AX. Now in this case, AX is a 16-bit register. So this will be added with memory pointed by SI, 16-bit memory pointed by SI. And then last is ADC 4000H comma BX. So here BX will be added with memory that is at 4000H. Then let us go to the next instruction, that is subtract integers, SUB. So this will subtract the source operand from the destination operand and replace the destination operand with the result. So destination minus source, and this will be going to the destination. And if borrow is required, the carry flag is, the operands may be signed or unsigned bytes, words or double words. And the flags affected, all the flags are affected: overflow, sign, 0, auxiliary carry and parity carry flag. So let us take example. Now here sub AL comma 45. So 45 is subtracted from AL. Then sub AX comma BX. BX is subtracted from AX. Then sub AL comma BX. So the contents of memory location pointed by BX, they are subtracted from AL and the result will be stored in the AL. Then sub BX bracket comma CL. Now here the contents of CL register, they are subtracted from memory location pointed by BX and the result will be stored in B. Then sub BX bracket comma CX. Now here the operation is similar, only difference is CX is 16-bit register, so contents of memory location BX and BX plus 1, they will be used in the subtraction. Then last sub EAX comma BA. Now here both the registers are 32-bit, hence 32-bit subtraction operation will take and the result will be stored in the EAX. Then subtract integer with borrow, SBB. Subtract the source operand from the destination operand and replaces the destination operand with the result. -1 if the carry flag is set. That means destination minus source minus the. Then if carry flag is clear, it will be same operation as the sub instruction. Then let us take examples. Here SBB AX, 0010. So this is a 16-bit operand. So that will be subtracted from AX register. Then BX is subtracted from AX in this case. SBB AX, then here SBB AL, BX. This is the memory location pointed by BX. So that will be subtracted from AL along with the carry flag. Then SBB BX, CL. So here CL is subtracted from the memory location pointed by BX along with the carry flag. Then SBB AX 4000. Now in this case, this is a memory location pointed by 4000. Contents are 16-bit contents, they are subtracted from AX register. Then the next instruction is INC or increment. So this will add 1 to the destination operand and it does not affect the carry flag, preserves the carry flag. This shows the use of INC instruction to update counters in loops without disturbing the status flag resulting from an arithmetic operation used for the loop control. Here only except carry, all other flags they are affected. So destination plus 1, that will be the destination. So example, increment AX will increment the AX register. Then INC EAX, it will increment the EAX register. INC BX, it will increment the memory pointed by BX register. Then INC SI, it will increment the memory pointed by SI register. Then decrement DEC, so it will subtract 1 from the destination operand and it will also preserve the state of the carry flag. So again the same thing as the increment for will be useful for the loop operations. Then destination will be destination -1. An example, decrement AX will decrement the AX register. Decrement EAX will decrement the EAX register. Decrement BX will decrement the memory pointed by BX register, and decrement SI will decrement the memory pointed by SI register. The next instruction is compare. So it will, this instruction will subtract the source operand from the destination operand and it updates the flags. So overflow, sign, 0, auxiliary carry, parity and carry flags, they are updated, but it will not modify the source and destination. So here if you look at the examples, compare AX, 0100. So it will subtract 0100 from AX. Now the result is discarded, but only the flags are. Similarly, here we are comparing AX and BX. Here we are comparing AL with 22, and here we are comparing BX with the contents of memory pointed by SI. Here we are comparing the BX register with the memory pointed by 0100 and 01. Then here we are having two registers which are 32-bit, they are compared. So in all cases, the subtraction of the source operand, the destination operand will take place, and only the flags are set. Subsequent jump or set instruction can test the flag. Then the last in this part is negate. Now this subtracts the signed integer operand from 0. So the effect is to change the sign of 2's complement operand while keeping its magnitude intact. So here the flags are affected. For example, here if you take NEG EAX, So EX is subtracted from 0. So we'll get the negative value, sign will change. So similarly, we can negate the AX register, BX register, AL or BL register. Then the MUL instruction, unsigned integer multiply. Now this instruction performs the unsigned multiplication of the source operand and the accumulator. So AL, AX or EX register. Here the source 8-bit is multiplied with the AL register and the result is stored in AX register. And when the source is 16-bit, will be multiplied with AX register and the result will be stored in DX and AX register. So DX will have the MSB and AX will have the LSB part, the word. Then when the source is 32-bit, it will be multiplied by EX register and the result will be stored in EDX and EX register. So the MUL instruction sets the carry and overflow flags when the upper half of the result is null. Otherwise, the flags are clear. And the other flags, the sign flag, zero flag, auxiliary carry and the parity flag, they are undefined. Let us take example. So here, the first example, multiply 35H with 25H. So first we load the 25 into the CL register. Then we load the 35 into the AL register. And then we use the MUL CL instruction. So this will multiply CL with the AL register. So AL and CL, they are multiplied and the result will be stored in the AX register. And then we halt. So the result will be available in AX register 07A9. Then next we multiply 2535 with 3535. So in this case now, since these are both 16-bit numbers, we'll take 16-bit registers here. So move CX 2535, move AX 3535, and then we use the instruction MUL and then halt. So the result will be available in DX and AX register. So the result is 07 BBH and AC F9, the hexadecimal result. Then the signed integer multiply IMUL. So it will perform the signed multiplication operation. It has three variations. First is one operand form. So in one operand form, a byte word or a double word located in memory or in general register, and this instruction uses EAX and EDX as the implicit operand in the same way as the MUL instruction. Then two operand form. So one operand, source operand, may be in any general register while the other may be in memory or in general register. And then there is a third form, that is the three operand form. Here two are sources and one is the destination. So one of the source operand is an immediate value stored in the instruction, and the second may be in memory or in general register. The product may be stored in any general register. The immediate operand is treated as signed, and if the immediate operand is a byte, processor automatically sign extends to the size of the second operand before performing. So in this way, the sign multiplication will be with the IMUL. Let us see example. So here we are taking two negative numbers, minus 2535 and minus 3535. So first we load the first number in CX register with move CX comma 2535. Then here you have to change the sign of this. So we use the instruction neg negate. Then we move the second number 3535 into AX register, and again we negate this because here it is minus 3535. Then we use the IMUL instruction. Now since both are negative numbers, the result will be positive, which will be available in DX and A. So the result is 07BB ACF9. So that will be the IMUL. Then the next instruction is DIV or division instruction, unsigned integer division. So here it performs the unsigned division of again AL, AX and EX registers by source operand. So accumulator is divided by the source operand, and the dividend is twice the size of the divisor. The quotient and remainder have the same size as the divisor. So here you can see the table. The operand size divisor, if it is byte, so dividend will be AX register because it is 16-bit. The quotient will be AL register, which is 8-bit, and remainder will be H register, which is again 8-bit. If the operand size is word, that is 16-bit, then dividend will be in the DX and AX register, which is 32. Will form 32. The quotient will be in AX register and remainder will be in the both are 16. Then if the operand size is double word 32-bit, in that case the dividend will be in EDX and EAX register, and the quotient will be in EX register and remainder will be EDX. In this way the division will be. Let us take example. So here we are dividing 3535, that is 16-bit number, by 55. So first we move the 55 into CL register and then move AX with 3535, that is the 16-bit number. Then we give the instruction DIV and hold. So now the quotient will be available in the age register is A0, remainder is. Then IDIV, that is signed integer divide. So it will perform the signed division of accumulator by the source operand, and the IDIV instruction uses the same register as the DIV instructions. Here if we take AX divided by the 8-bit source, the result will be in A and remainder will be in AH. Then DX AX, that is 32-bit divided by those 16-bit, quotient will be in AX, remainder will be. Let us take example. Now here we take minus 26F7 divided by 55. So here the dividend is negative. So both quotient and remainder will be negative now. So first we load the quotient in the AX register and then we negate it. Neg AX will negate the dividend. Then move CL 55, that is the divisor. Then IDIV C will perform the signed division. Then after that we'll have to negate the quotient as well as the remainder. Negate AL, negate A, both will be negated, and result will get quotient as minus 75 and remainder as minus 1. With this we come to the end of this video. If you like the video, press the like button, share with your friends and subscribe to our channel Engineering and Technology for You. And don't forget to press the bell icon to get notifications for our future videos. And thanks for watching. Have a nice day.